Go ahead and get started. Good afternoon, everyone. Welcome to the A. James Clark School of Engineering 2021 Innovation Hall of Fame induction ceremony. It's great to see everyone in person and have the opportunity to meet you. And it's also great to have others that are tuning in online. For those that haven't met me, I'm Samuel Graham, the new Dean of the Clark School of Engineering. One of the things I want to say is that when I first arrived here at the Clark School, before I started as Dean, I came with my family to check out the campus. And the first time coming into the buildings, I actually walked directly through this hallway. And I was intrigued by seeing the pictures that are here on the wall. I knew that this was an Innovation Hall of Fame. And one of the things that intrigued me is that I'm always excited to meet inventors. Because inventors don't just create by changing the way that we do things based on the laws of physics. They don't just come about solving minor problems, but they see the world differently. They visualize problems, they visualize how things can be, and they use their knowledge, their perseverance, and their innovation and ingenuity to change how we behave, change how we can operate, and change how we can do things in the world. They see vision of the things that don't exist today, and the vision of how the world can be a better place. I'm happy to say that we're going to continue to invest in our students to teach them how to be inventors, to allow them to grow in these aspects as we continue to develop our educational aspects here in the Clark School of Engineering. But if you think about it, the Clark School has had a rich history of producing incredible innovations. From pulse Doppler radars that are used by our military, the universal product code that is used on almost every item that we buy, flexible coronary artery stents that help people live longer and have healthier lives. These are just a few of the innovations that we celebrate here in the Innovation Hall of Fame. And today we add one more, Dr. José Reyes and his work on nuclear power. When the world needs engineering leadership, it comes to Maryland. And we celebrate engineering leadership by those that are here in our Innovation Hall of Fame. That's what it's all about. Before we continue with today's program, I'd like to acknowledge a few people. First, I'd like to acknowledge Dr. Darrell Pines, President of the University of Maryland, College Park. I'd also like to acknowledge many former Hall of Fame inductees who have joined us today, either in person or virtually. Angel Bezos, Nate Bluser, Reinhard Rademacher, Bob Fischel, Rajiv Laroya, Raymond Kryzik, Alex Severinsky, Robert Briskman, Ashish Bagai, Naomi Leonard, John Barris, Don Willis, Gary Eden, and Craig Lauer, the son of the late George J. Lauer, our 1991 inductee. I'd also like to acknowledge the committee that spent the time to go through the selection process and come up with the inductee that we have today. The committee was led by Nate Bluser, and I'd like to thank him and the committee members for their commitment to Maryland engineering and this tradition of the Clark School. I'd also like to give thanks to the Berman family, including Scott, Brian, Marcia, Rachel, and Danielle. Danielle is a senior at the University of Maryland, majoring in family science, and we're glad to have another Berman Terp in our ranks. Thank you. So more than 30 years ago, Stanford Berman, a 1950 Clark School graduate, proposed an Innovation Hall of Fame. He wanted to recognize the contributions of Clark School engineers to our profession and to our society. Stanford and his wife, Marilyn Berman Polans, herself a former associate dean of the Clark School, helped establish an endowment to fund the Innovation Hall of Fame. Today, the Hall of Fame is, in essence, a classroom for the world, where students, faculty, friends, visitors, and all others can come and learn about the impact of engineering and the engineers that have impacted and changed the world. We're honored to add Dr. José Reyes to our Innovation Hall of Fame. Now I'd like to welcome Scott Berman to speak on behalf of the Berman family.
Good afternoon, everybody. My family and I are very pleased to be here this afternoon. It's great to see so many engineering fans. My father graduated from the College of Engineering 45 years ago, or more than 45 years ago, with a mechanical engineering degree, went to law school, and then became a patent attorney in private practice at a firm with my grandfather and others. He was in private practice for 45 years and represented many engineers during that time. He also taught a course at the College of Engineering on patent law for engineering students, which was a very popular and well-attended course. My mother was a legend in her own right at the University of Maryland. After raising her family, my mother returned to Maryland for graduate studies, earning a master's and Ph.D. in higher education. She worked at the College of Engineering for many years, ultimately becoming the Associate Dean of the College of Engineering. My dad cared deeply about engineering. When my brother, sister, and I were growing up, my father often would point out things like aqueducts and bridges and explain in terms we as children could understand the engineering behind these man-made marvels. We would sometimes roll our eyes and grin, but as I look back on those times now, it really does illustrate my father's belief in the importance of engineering and that it should be appreciated and not taken for granted. My dad cared deeply about the Clark School, and he cared very deeply about creating an environment here that fostered innovation. He believed that recognizing innovators would raise the profile of engineering and help people understand why engineers make such a big difference in our daily lives. He also cared deeply for the engineering students who walked the Clark School's halls. He wanted to provide strong role models, signaling to the students what they can achieve through engineering. So he decided to endow this Innovation Hall of Fame, which I think we can all agree has succeeded beyond his wildest dreams. It is quite a legacy. If my father were here today, I think he'd be very pleased. Congratulations, Dr. Reyes. We're glad to welcome you to the hall. Thank you all for attending.
Thank you, Scott, for sharing your perspective on the Hall of Fame, and also thank you to your family's central role in establishing this event and this opportunity for the Clark School. It's now my pleasure to introduce Nate Bluser. Nate is a Clark School alumnus, Innovation Hall of Fame member, and chair of our selection committee. He'll share a note about Dr. Reyes.
Should be easier without the mask. Thank you, Dean Graham. As Dean Graham described, the Clark School of Innovation Hall of Fame, IHOF, recognizes innovation at conceptual or engineering design levels. The innovation's value is judged according to its benefit to society. Clark School alumni, students, faculty, and individuals with a strong connection to the Clark Schools are eligible for selection to IHOF. This year, Dr. José N. Reyes is selected to IHOF for co-designing the first modular nuclear reactor to receive approval from the U.S. Nuclear Regulatory Commission. This innovation was achieved through distinguished careers in academia and industry, all of which I'll highlight next. Reyes credits these achievements to his education at the University of Maryland, an MS in 1984 and a Ph.D. in 1986, both in nuclear engineering, and his mentor, which includes Mohammed Modaris, who directs the Center for Risk and Reliability. After graduating, Dr. Reyes studied reactor design for 10 years as a research engineer on thermal hydraulics in the Research Safety Division of the U.S. Nuclear Regulatory Commission. Next, Reyes joined Ohio State University, Oregon State University. I was worried about I'll make that mistake, and I did. Where he advanced it to the department head of nuclear engineering and radiation physics. Also, he served as principal investigator in the design and certification of test programs for the AP600 and the AP1000 reactors, sponsored by the NRC, the U.S. Department of Energy, and Westinghouse. Reyes is the inaugural recipient of the Henry and Janice Schuette Endowment Chair Professor at Oregon State University. Currently, Dr. Reyes is Professor Emeritus at OSU. About 20 years ago, to achieve 24/7 reliable and carbon-free electric power generation, Reyes, as Chief Technology Officer, and colleagues founded NuScale Power. Their innovative approach is the small modular reactor, or SMR, assembled from 12 independent reactor modules interconnected with the reactor's internal electric grid. For minimum cost, the reactor modules are fabricated on the factory assembly line. For safety, the SMR reactor is water-cooled by a passive process using gravity and convection, which is more reliable than electric pumps. Saliently, the reactor modular design enables independent servicing of each reactor module, which avoids reactor shutdown during module maintenance, facilitating 24/7 reliability. This is very important. It should be noted that solar and wind generation also requires reliability. However, they are subject to outages. These outages can be circumvented by adding a small modular reactor to intervene during power outages, thereby achieving a 24/7 reliable carbon-free electric grid with solar and wind generators. That's a nice freebie from the nuclear reactor. On August 2020, NuScale Power made history by receiving NRC's approval for the design of a full-scale commercial SMR plant with up to 12 modules, generating up to 600 megawatts, with each module capable of generating 77 megawatts. Backed by investors from Fluor Corporation and over $242 million in grants from the U.S. Department of Energy, NuScale Power is on track to build a reactor at the Idaho National Laboratory, expected completion in 2029. Concurrently, NuScale is starting production of individual reactor modules. Each module unit will produce up to 50 tons of hydrogen per day, intended for transportation using hydrogen fuel cells. Dr. Reyes is a fellow of the American Nuclear Society and a member of the National Academy of Engineering. He has given keynote addresses and lectures to professional nuclear organizations in the US, Europe, and Asia. He authored numerous journal articles, technical reports, including a book chapter on small modular reactors for the American Society of Mechanical Engineers Code and Standards Handbook. Dr. Reyes is an expert on nuclear plant scaling, passive safety, and testing. He has about 110 patents granted or pending in 20 countries. For these accomplishments, we are pleased to welcome Dr. José N. Reyes to the Clark School Innovation Hall of Fame.
So it's a little bit off script, but in my research area, we're really big on electrification and trying to do things with cars and looking at electric industrial motors and things like that. Now we know where we're going to get the power from, so thank you very much. Okay, so thank you very much, Nate. Now I'd like to take the opportunity to introduce the University of Maryland's president, Darrell Pines. As many of you know, Darrell Pines was the dean of the Clark School for 11 years before becoming president of the University of Maryland. As dean, Darrell led the Clark School to a larger and more diverse and accomplished student body, similarly a more diverse and accomplished faculty, greater research expenditures, and more research solutions that impact the world. He was elected to the National Academy of Engineering in 2019 for inspirational leadership and contributions to engineering education excellence in the United States. Please welcome President Darrell Pines.
So how about a round of applause for Dean Sam Graham for coming here from Georgia Tech. Sam is very much smarter than I am. He's going to do a lot of great things, and he's going to ask me for a lot of money. So I'm really happy to support Sam, and Sam has been fantastic. I also want to recognize Nate Bluser, who's been doing this job for how long, Nate, chairing this committee? 14 years. Give him a round of applause. Look at all the incredible people that he has chaired that has gone to the Hall of Fame. And so where's Craig Lauer? Where is he? Is he here? So I actually did something special today. I actually put on the barcode socks today in honor of, look, barcode socks in honor of George Lauer, who has come to this event since I was dean 9 consecutive years, and unfortunately he passed away a couple of years ago. And I did it in honor for him because it means a lot to me what everybody has accomplished in this Innovation Hall of Fame. So thank you to the Berman family for doing this. And congratulations. Today we honoring Dr. José Reyes, who has made and continues to make a tremendous contribution to the field of engineering and to the engineering community. I am extremely grateful and honored as the president of this university, as the former dean, to host here at the University of Maryland alumni of such a supreme caliber as you, Dr. Reyes. Dr. Reyes today joins other innovators here on this wonderful Innovation Hall of Fame. Dr. Reyes today joins them as a pantheon of excellence. The Innovation Hall of Fame is all about excellence in innovation. So we would like now to honor him. So I'm going to ask him to please come to the stage. Please give him a round of applause as he walks up here. And the citation reads as follows. This medal is presented to Dr. José Reyes for his work co-designing the first small modular nuclear reactor to receive United States Nuclear Regulatory Commission design approval. Congratulations. Now, this is the first time I've ever had to do this because I was dean and I didn't have to do it. So let's make sure I do it right. All right. Congratulations.
Thank you so much.
Now, before we turn it over to you, Dr. Reyes, are we going to let him speak now, or are we going to do the plaque? Do the plaque first. Okay. So if I could have, where is it at? It's over there. Okay. If I could have you go over next to your plaque. So another tremendous tradition of this ceremony is the installation of the plaque honoring the accomplishments of the inductees. Dr. Reyes will, and I'll come over because I'm supposed to help you, just in case like something's going to go wrong, and which we know it isn't. Dr. Reyes' plaque will live here in the Innovation Hall of Fame hallway in the Kim Building alongside many of the other engineering pioneers. If you're in attendance today or you're on campus in the near future, please pay a visit to this incredible place. So I'm going to come over now. So I'm going to count down 3. So 3, 2, 1. Now we're going to hear from Dr. Reyes. Please welcome the 2021 Innovation Hall of Fame inductee, Dr. José Reyes. Congratulations.
The energy that powers us has changed over time. Innovation, ingenuity, and curiosity transform how we fuel our lives, allowing us to do more, to be more. Today, reliable energy enables many to live the human experience to the fullest. But not all have access. We all deserve to experience what it means to truly be human. And yesterday's energy has done all it could. Once more, innovation, ingenuity, and curiosity conspire to break through. It's time we outgrow what we think are our limits, to open our eyes to a better path toward the energy we need. A better kind of energy for humankind. Smarter, cleaner, safer, and cost competitive. It starts by reimagining what's capable and creating energy that can take us further. It starts with us, for all of us. NuScale, power for all humankind.
President Pines, thank you so much for your introduction. Dean Graham, thank you so much. Nate, thank you so much for your service to this committee, and I'm floored, just truly honored by this time. Faculty members, colleagues, previous recipients, family, thank you so much for being here. I'm just so excited, and I have to start by thanking Donna, my wife, who's, yeah. Donna has supported me, encouraged me throughout these past 45 years of marriage, and we have 45th anniversary coming up here next week. And so I wouldn't be, NuScale wouldn't be here, and I wouldn't be receiving this award if it had not been for Donna's amazing encouragement. I thank my family from Oregon and from Florida, from Texas, from Philadelphia, from all over. Thank you so much. Thanks for being here today. This is really a special honor, just you being here. I thank my colleagues from NuScale, from NuScale over here, and Oregon State University for dedication, collaborative spirit of innovation. And of course, I thank my church family and the many examples of integrity within our industry who have served as examples for me. So I'm going to start with a short innovative story. A little bit about, I graduated from University of Maryland 35 years ago. And you may be wondering what happened after I left, Gary. So I'm going to fill you in. I'm going to fill in the gap now. But basically, I was so impressed by the program here, and in particular, Y.Y. Su was my major professor. And Y.Y. said, if you want to make an impact, you really should go into academia. You should really teach others. And so I really took that to heart and decided I would look for a faculty position. And I found a great position at Oregon State University. And he said, remember, Jose, whatever you do, if you build it, they will come. I said, I think I've heard that before. I said, if you build it, they will come. And of course, at University of Maryland, we had a really nice integral test loop at the time that I got to work on, which was just wonderful. This thermohydraulic test facility to get a real sense of how things work. And so I said, well, I'm going to build one of those when I get to Oregon State University. So I got there, and this is in '87. In '88, I received my first grant. It was a graduate fellowship grant that I received for $4,000. I said, man, I got $4,000 just to do my research. This is awesome. So times have changed. It was 35 years ago, all right? So I said, well, what I want to do is I want to build a glass loop so I can simulate natural circulation heat removal from a nuclear reactor. So that was kind of a novel thing. To use, you're not using electricity, you're using this natural circulation. This was before things were called passively safe. So I got the $4,000. I said, I need some glassware. So I went down the street to a company called Teledyne Watchang at the time. And he said, hey, do you have some glassware that I can build this loop? I got $4,000. He said, oh, save your money. We'll give you all the glassware you want. Just bring some students in a truck and we'll load you up. And so we went there with some students. We got all the glassware to build this test loop. And then I said, well, this is great. Now I've got glassware, I got $4,000. I'm going to go to Portland General Electric and tell them what I'm doing. So I went to PGE. They said, this is a great idea. We'll give you $50,000 a year for 3 years. I said, this is amazing, $50,000 a year for 3 years. Fantastic. And so they said, you'll have to do a scaling study to show that what you build physically represents the real world. So did this little scaling report, and I came right here to Washington, D.C., and I presented a paper for the American Nuclear Society National Conference. And in the audience were some folks from Westinghouse. And they said, hey, Jose, that's kind of a neat idea. You think you could build a facility for us or do a scaling study for the AP600? I said, sure, no problem. So we went ahead and signed a contract, and that went from a scaling study to a $1.5 million contract, which then grew to an actual 1/4 scale test facility for about $5.5 million. So that $4,000 starting to grow. So that was kind of really an insight of you can actually leverage, if you got some good research going. So soon after that came the AP1000. They said, hey, we want you to do the AP1000 now. So that was additional funding. The NRC came in and said, hey, we want to do some confirmatory tests in your facility. So we did that. And so we had built this reputation of being able to build high-quality test facilities for nuclear power plants, for safety testing. So that was really exciting to me. But finally, in 2000, got a grant from the Department of Energy to look at a small reactor. We called it the Multi-Application Small Light Water Reactor, the MASLAR, which didn't flow off. We didn't have marketing back then. It was just the MASLAR. So we came up with a design concept for that, and we actually built it from 2000 to 2003. We ran the first test in that facility, and we were amazed. The safety that we achieved in that test that was performed in 2003 was unheard of. We had this tightly coupled containment to the reactor vessel, and it basically just kind of was a self-healing process. Within a few minutes, any event would be over. Any break on the primary side was basically captured and cooled down. So it was huge. It was a tremendous result. In 2004, I spent a 1-year sabbatical in Vienna with the IAEA, which was, we'll remember that forever. And I met with delegates from different member states. And what I kept hearing was, we really need nuclear power in our country, but we can't afford a 1,000-megawatt plant, and we don't have the grid to support 1,000 megawatts. So we need something smaller. And oh, by the way, we need clean water. I heard that over and over again. So when I came back to the United States in 2005, I said, we've got this small reactor here. How hard would it be to move this from the lab to the market? It's hard. It was pretty hard. So we did that. We spent 2 years. I got 3 base patents out of the work that was developed there. And we were investment ready in 2007. We started meeting with investors, and that was a new experience for me. Had not done that as an academician, not so much. So going around looking for investors, and finally got our first investor in 2008 of February. We opened the doors to NuScale Power. And one of the very first phone calls I made was to Mohammed Modares. So Professor Modares, of course, was on my committee when I graduated, and it was really so helpful because I said, we need to start our probabilistic risk assessment. And so he volunteered right away and agreed to do that and got some really amazing results. And this is really fairly preliminary, but we knew we had something special. Once I got those results, I realized in the field of safety for nuclear power, we really had something very special. And so we have stayed in touch throughout all these years. So I co-founded the company in 2007, the NuScale Power, so just 2 of us. And we had the 3 base patents, and today we have 628 patents, either pending or granted in 20 countries. And that's because of the innovation. We have this DNA in our company of innovation. About 40% of our company is either 20 or 30, so they're in their 20s and 30s. And it's just an exciting environment to be there. There's a level of excitement and innovation, not just in nuclear, but in digital I&C, in a whole range of applications, which some of them are not related to nuclear at all, but have that connection. And our view, in terms of the size of the company now, we're about 460 employees now in 5 offices in the US. We opened an office in London, and there's just so much going on right now globally. Recently, President Biden, with the White House announcement in Glasgow at COP26, made an announcement that said, hey, the US teamed with Romania, teaming with NuScale Power, is going to build a 6-module plant in Romania. That was huge. That was huge for us. And since then, we've been flooded. When I go back to Corvallis, we've got a series of meetings with a lot of different groups interested in technology. So we started with a $4,000 grant and an idea. And so think about that. When you think about innovators, your students who come up with an idea and they say, we need a little bit of funding. And I got some great tours here of some of these incubator type situations. It really does, it really can make a big difference. So to date, NuScale has received over $1.3 billion in investment. And we continue to garner investment from many, many investors around the world. And we're the first and only small modular reactor to have been approved by the US Nuclear Regulatory Commission. So that's kind of my innovator story. But I want to talk about the promise of innovation and what will be the outcome of this. And this is where we're working very hard. We view nuclear power to be much more than just electrical power production. Global energy poverty, about 5.9 billion people live in energy poverty. About 800 million people don't have access to clean water. Air pollution contributes about 5.5 million deaths globally each year. More than 1 billion tons of food is lost or wasted for lack of refrigeration, just having power to get it from the farm to the market. So those are the challenges. But not only do we have to meet those challenges, we have to do it using carbon-free energy. And that multiplies the challenge tenfold. So we really view our technology solution as our mission to provide clean nuclear technology for the production of electricity, heat, and clean water to improve the quality of life for people around the world. And that last part, to improve the quality of life for people around the world, that's what resonates with our engineers. That's what they're doing. They want to change the world. And we're empowering them to do that. And they are stepping up. So we've done multiple studies. First of all, of course, it is carbon-free power. You know, a 12-module NuScale plant will produce 924 megawatts gross, which powers over 700,000 homes with carbon-free electricity. This would reduce about 8 million tons of CO2 emissions per year as compared to coal, for example. Or it's about the equivalent of taking 1.7 million cars off the road each year. Hydrogen production, this is where we've been working on this since 2014, looking at combining a NuScale plant to high-temperature steam electrolysis. We are approved for off-grid operation. We're the only nuclear power plant, commercial nuclear power plant, that doesn't require external power for safety. We don't need to be connected to the grid, which means we could be located at some of these coal-fired plant sites at the end of the line. We can be located in, near different processes because we don't need to be connected to the grid for safety. One module will produce roughly 50 tons of hydrogen per day. So that's enough to power about 38,000 fuel cell vehicles or 1,500 long-haul fuel cell trucks. So now we're able to start infiltrating the transportation sector. Now it's not only electricity, but also transportation. Clean water. We did a study with a company called Aquatech using their technology. One module could produce about 77 million gallons of desalinated water per day. 4 modules would be enough for the city the size of Cape Town, South Africa, almost 4 million people. So we can meet those daily water requirements. We're seeing practical ways of achieving these goals in our lifetimes. So we did a study on oil refineries. We got asked this question, well, if you connect the 8 modules to a 250,000 barrel per day oil refinery, how much could you reduce CO2 emissions? Well, it turned out to be about 40%, just by providing electricity and process heat. About 200 metric tons reduction per hour. So I believe that innovation is born of your passion and your tenacity for solving a problem that, from your perspective, is of critical importance. Executing on your passion requires a strong educational foundation. And so I'm grateful to the faculty at the University of Maryland for their dedication and their mentorship. You inspired me to pursue a career in academia, and you truly have fulfilled the ancient proverb, as iron sharpens iron, so one person sharpens another. So thank you so very much for this tremendous honor, and I'm just blown away by all the kind things that you said. Thank you so much.
opportunity to allow the audience to ask a few questions.
Wonderful. I got 6 more pages, you know. No, feel free if you have any questions.
When will that first approved reactor come online?
So our first project is with the Utah Associated Municipal Power Systems, and that's scheduled for the first module to be online in 2029. But recently we had the announcement with Romania that's interested in power by 2027 or 2028. So, yeah, part of what will happen in terms of the process, we have completed 2 manufacturing trials, one at BWXT and in Lynchburg, and another one which has been done at Doosan in South Korea. So part of it is making sure you got the manufacturing process right. The second part of it is that the site needs to be prepared. And so the owners of the site will prepare what they call their construction operation license application, and they need to submit that to the NRC. So what they've done on the site are things like already paving roads, digging boreholes for the hydrology, for seismology. They've built the meteorology towers. So all that's happening right now. So there's activity at the site. So that happens all in parallel. So we'll pursue that course, and we're certainly, in terms of our module delivery, we can start delivering modules as early as 2027. But the customer is not retiring their coal-fired plant till 2029. Yeah.
Is every module self-sustainable? Meaning, how does it scale if I add modules with respect to energy production and cost?
Yeah, so,
Can I have production just by one module?
say again, what production by?
Energy production by just one module.
So one module, right now we have focused on 3 different product offerings. The 12 module plant, which is 924 megawatts, the 6 module plant, which is the 462, and the 4 module plant, which is 308 megawatts. In terms of the interest we're getting right now, it's mostly for the 4-pack and the 6-pack, because these are ideal for coal-fired plant replacements. A single module would work well with the remote locations where they're using diesel. You know, they're paying 25 cents per kilowatt hour. So that's something we haven't done the design in terms of the building for that. But right now we have the 3 product offerings that we've publicized.
The size of the building and the cost and everything else scale up linearly, or is not?
No, so it's not linear, but
So having one single is not a very good idea, right?
it depends on the location. Yeah, it depends on the location. If you're using diesel, we could certainly look at that. Yeah, you're welcome. Yes.
I'm curious to know about the scalability in the opposite direction from large down to small. And how small do you think you can make a practical modular reactor? And what would the transportability or the relocatability of such a device be?
Yeah, so for our particular design, just to give you a sense of size, of scale, it's about 22 meters in length. It's a big cylinder, and about 4.5 meters in diameter. So it's a reasonably good size, and each one is 250 megawatts thermal, producing about 77 megawatts electric. In terms of the smaller sizes, the microreactors as they're called, you're probably hearing a lot about microreactors right now. A lot of work going on in that arena, and those are more from the 1 to 10 megawatt sizes, and those work well for remote communities and things like that. So you'll be learning more about what's happening in the microreactor space. But the Department of Energy is very interested in moving that forward, and some of those would be mobile reactors that they can actually use and move from one location to another. And so the mining industry, for example, looks at those very favorably. There's other industries, and even for emergency situations, where these microreactors might be suitable. Yeah.
Jose, one question. Once you're fully operational and commercial and everything, what's the time frame from when a utility places an order to commercial operation anticipated?
Yeah, so the first plant, of course, will be very telling. And so we're really focused on that first plant, because if you ask our CEO what he worries about, he says, we have to deliver that first plant on schedule and within budget. And that's absolute in order for us to build any more plants beyond that. So we'll learn a lot in this first deployment, what the schedule would be. But in terms of first pour of concrete, of safety-grade concrete to operation, that's about 3 years. So the modules are designed for 60 years, and the building is designed for over 100 years. So you can actually replace a module in the building.
Okay, let's thank Dr. Reyes once again. As I said before, I always love listening to inventors. You learn a lot. You learn about the story, but and also just the impact that's very timely for what we need today in society. So thank you very much for the many years you've put in and the determination and the results that you've come up with. We're gonna benefit from this all around the world. So thank you very much once again. So with that, it concludes today's ceremony. We would like to welcome you to attend a reception right outside, and you could have some more time to spend with Dr. Reyes. Thank you very much for attending.